All right, here we go with the chemistry of life review. Uh, Chemistry is the basis of life, and so it's fitting that we start with this section because it kind of gives the foundation for all the other sections. Um, on the screen, you have all these food items because a lot of this chemistry of life has to do with molecules that we associate with food. And I think the food items show the wide variety of different kinds of molecules you can make using the same basic atoms as we'll talk about, right? You have your lipids group, you have your proteins, you have your carbs. I didn't put DNA on here because people don't usually think of that one as being a food. And then of course you have water, which isn't a food necessarily, but it is super necessary. And one of the first things that we ended up talking about. So here we have just a kind of overview of like these big statements that hopefully make sense already, but just to put them out there because they're kind of woven in throughout the whole year and never specifically said. But we have the idea that life is built on a hierarchy of structural levels, and we've seen this before. How each level builds into the next. Each level has its own properties that then affect the level above it, meaning that all the properties of the organism can be eventually tied back towards the properties of the atoms that make up the organism, right? And so then that leads to the next idea that in order to live, we need constant input of energy and exchange of molecules, that whatever molecules are in you had to come from the environment and be assembled by your body in order to live. There are a lot of those elements, but the main ones are down here. Carbon, nitrogen, hydrogen, oxygen, phosphorus, and sulfur. There's a lot of other ones that you need in a lot more smaller amounts, but most of the molecules that we talk about have these in them. And so one of the first really big idea that we started was that the chemical properties drive the biological function, right? And so we want to know what atoms are in the molecules. And in particular, a property of polarity is going to be important, which is derived from the structures of molecules. And then once you understand that idea, then that helps to understand how they interact with each other to give their functions, right? And so water is a great example of this, and there's a lot of reasons why water is important. But the structure of water gives it all these properties that make it biologically important. On the left here, we have a methane molecule. And on the right, we have the water molecule. And the main difference is the type of bond in there, that on the methane molecule, the shared electrons are in the center of the space between the carbons and the hydrogens. They're evenly shared or equally shared. Whereas in the oxygen, the electrons are all towards in the water, the electrons are all towards the oxygen. And that is something that is important and different because that makes water something polar, whereas methane is non-polar, right? This is all based on the properties of the atoms. We don't have, if you want to go into this more, you can go back to some of the first lectures. But the basic idea is that each atom has a particular property called electronegativity. And the higher the number is on this side right here, the stronger that element is or atom is going to pull on the electrons when they're trying to share, right? And so we want to know the difference between those partners. If they are sharing, are they sharing equally or unequally? And so you get this kind of spectrum of an example where you have two atoms that are very close in their strength. For example, hydrogen and carbon. Those are pretty close, so they're going to share equally and make a non-polar covalent bond. But then you have the next one where you have a strong versus a weaker one. Not too strong and not too weak. Again, maybe something like oxygen and hydrogen now. Oxygen being a 3.5 compared to the carbon's 2.5 from last time, right? And so that means that the oxygen is going to hog some of the electrons. And then if you get really crazy with it and you have a really strong atom with a really weak atom, such as chlorine and sodium, you get a huge difference between their electronegativities, and that would end up being an ionic bond because in this case, the chlorine is basically just going to take the electrons. It's not even going to share anymore. But the polar and the nonpolar covalent are important because this is where a lot of the properties of water come from. When you get your oxygen that has more electrons, it's going to going to be called partially negative. It's not fully negative because it's still sharing, but it's mostly hogging them. And then you have the hydrogen that has basically lost an electron almost, which makes it partially positive. This gives the atom poles. There's a negative pole and a positive pole, right? And so that's kind of like a magnet. We call it a polar molecule, and the magnets are going to attract each other. And the attractions between them are what are really going to give the properties of water due to what's called hydrogen bonding. There are other things out there that you might learn in more advanced chemistry classes, but for our purposes, hydrogen bonding can explain all of this, that the partial positive here on the hydrogen is going to be attracted to the partial negative of the oxygens. And so you have, in essence, all these tiny little magnets when you're looking at a, like say, a glass of water, right? And so that makes water a liquid because the molecules are attracted to each other strong enough to keep them from flying away as a gas. But they are weak hydrogen bonds, and so they're not strong enough to make it a solid, right? This helps it to dissolve things because the partial negatives, especially of the oxygen, will seek out any partially positive part of another molecule, or say the sodium atom of sodium chloride, and then that will make the sodium detach from the chlorine, and then we would get the salt to dissolve. Cohesion and adhesion is responsible for things like surface tension and for capillary action because the water molecules are attracted to each other. They're also attracted to a lot of things around them, and so you get surface tension and capillary action. Ice floats because the hydrogen bonds structure the molecules in a way that makes them bigger than they were when they were a liquid, which makes it less dense. High specific heat means that you can put a lot of heat into this and the hydrogen bonds will absorb it, which means that water stays cool. And so as the land gets hotter and the cool water stays cool, it keeps the land from getting too hot, which is why places near the ocean are usually not very warm or not extremely warm or extremely cold, because again, the water does hold on to a lot of heat. And so when the land starts to get cold, the water will keep it more warm than it would have been if there wasn't any water around. High heat of evaporation means that if you put enough energy into this, it'll finally evaporate, but when it does, it carries that energy away. For example, when the sweat on your skin evaporates and it cools you down, and that's very helpful. So all of that is because of hydrogen bonds. All of that is because of the polarity of the molecule, which is because of the electronegativity of the atoms, and there you have that hierarchical structure, right? And so that's a big idea, that the structure of the atoms or the molecules is going to give them their properties. Now, then that went into all these different food types of molecules. And again, the idea here with food is that your food is made up of all these different combinations of molecules. Your job is to digest them and to break them down into their tiniest little parts that can then be absorbed into your cells. And then your cells will take those parts that you just disassembled and then reassemble them into other things that you might need. And of course, anything that you don't need gets eliminated. This is based on the idea of polymers, that we have basic molecules, small monomers, single pieces, but then we can take those single pieces and put them into long chains called polymers, and then those long chains have different properties compared to their original monomers, right? And so for the digestion, when we're talking about breaking down our food, this is where we're going to use a hydrolysis or digestion reaction. And the enzyme, of course, is needed to inject water into this bond, and it would separate out one of the monomers, and then this monomer could then be used to go off to do whatever it is that you want it to do. Now, that polymer had to be made. So sometimes we're going to take our monomers and we're going to join them with other monomers, and that's called a dehydration reaction, sometimes condensation reaction. Another important word here is the word synthesis. We're going to make things, right? We're going to build something. And so by removing water, the dehydration reaction, we get this covalent bond to be made, which again, later can be broken if necessary. So then the idea is that what are these monomers? And there's 4 different types of monomers or macromolecules that have their own monomers and polymers. Lipids was the first one we talked about. The main one that we're going to talk about right now is for the energy storage. We'll talk about cell membranes and those things later, right? They have their own section. But why is it such a good storage molecule? And it's because of its structure, that it is made up of these long chains of hydrocarbons, because they just have hydrogen and carbon. And hydrocarbons are non-polar, which means that their electrons are shared right in between the atoms. And this means that when you were to maybe break that bond, the electrons can release a lot of energy. And so you get a lot of energy out of that. The longer the chain is, the more energy you can store. And so then the structure, again, gives it its properties. But then there's other properties of lipids, like the saturated versus unsaturated, where if you have your hydrocarbon chain and it's full of hydrogens, there are 0 double bonds. There should be a line right there. All hydrogens, no double bonds. This is a saturated fat. This is going to make straight chains and more solid types of lipids like butter. Whereas you have right here, some hydrogens missing in a double bond, which gives the chain a kink in it and makes it change its shape, which makes it harder for it to stack, and that gives it a more liquid consistency, right? So again, the idea is that the structure of the molecule is going to affect its function in a biological setting. Then we have sugars. Sugars are made from the same molecules as lipids, but this time they come in rings instead of long chains, and they're usually only 5 or 6 carbons long. The big one is glucose. There are other ones like fructose. And so each of those has their own properties, which again, glucose, of course, is the one that we use mostly for cellular respiration. Fructose, which comes from fruit, can be used as well with a little bit of processing by your liver to convert it into things that are more useful. But still, there's energy stored in there just like any other sugar. But then you can take these monomers and start to join them through our good old dehydration reaction, where we're going to remove those atoms to make water. An enzyme is doing this, of course, which makes a very strong linkage here. And you take a glucose and a fructose and you get sucrose, plain old table sugar, right? And so the table sugar has slightly different properties than the glucose or the fructose alone, because now it's 2 things that are joined and they're going to react differently. There's lots of other, these are what we call a disaccharide, because there's 2 sugars. There's a few other ones. If you take 2 glucoses, you get maltose. I think a glucose and a galactose gives you lactose. In any case, there are a lot of different ways to combine them, which gives you variety and the flexibility in an organism to build lots of things. Of course, we could take the glucose and put it into a long chain that we call a polysaccharide, where we have starch up here, which is, of course, a great energy storage molecule, because each one of these glucoses can be removed by a digestion reaction and then used as energy, 1 piece at a time. But then the idea that changing the structure changes its function, because down here in cellulose, we have different linkages here that alternate. They're not all the same anymore. And this prevents our human enzymes from breaking this down. And so cellulose is not a great energy storage molecule for humans. It does make a very strong fibrous molecule, because having the alternating OH up sometimes, and the carbon with the OH up and the carbon without the OH down. The alternating pattern allows it to make these hydrogen bonds, which make it a very strong interactions between these long chains. And then you end up with this fiber. And that's one of the reasons why we call cellulose in our diet fiber, because it's kind of fibrous in that way. DNA and RNA, we have a whole section on this, obviously. So the big idea, of course, is that we have our nucleotides, which are monomers, and the nucleotides would get joined together to make a polymer that we would call a nucleic acid, that are huge and long chains of nucleotides. We have, the big thing here would be the differences between them, and those come from the deoxyribose has a missing oxygen on there. And then in the ribose, we have an oxygen right there, and that makes it form a double helix when you're in DNA, and it's only a single strand. Where in RNA, there is the whole like T versus U situation that you should remember, but there are these 3 differences chemically between DNA and RNA, which give them their different functions. Finally, proteins. Proteins are the biggest group. They do all of these different things. We talked about proteins for a very long time. The idea here is that proteins are made out of monomers, in this case called amino acids. There are 20 different amino acids because there are 20 different R groups. The carboxyl and amino and central carbon part, those stay the same. That we would call that like the backbone. And then we can take these and join them together. Here's the 20 different ones. Each of the R groups have a different chemical structure to them. Some of them are nonpolar, some of them are polar, some of them are charged, some of them are not, some are big, some are small. These are all going to be things that make a difference when they're trying to fold and pack together as a full protein, right? So we take those 20 different amino acids and we can join them using our good old dehydration synthesis, where we have the backbone that just keeps repeating, and then sticking out we have R groups, and those R groups are going to interact with each other. And so again, we have this is going to help the proteins fold. The structure and the shape of the proteins, if I'm sure you remember, are super important. So the first thing that's important is the order of the amino acids that they are linked together in, right? And so this is all based on the DNA. Then we have the secondary structure, which is probably not going to come up too much, but there are small regions where you get little helices, or flat things that we call beta pleated sheets. These are small interactions, and they're very complicated, and it's very unlikely that you'd be asked about them. The big one is the tertiary structure, because the primary structure plus the secondary structure ends up making different amino acids close to each other or far away from each other. This is all happening in water, and so the nonpolar amino acids, the ones with the nonpolar R groups, are going to be unhappy in the water, and they're going to start to clump together like is being shown here. And the only way for those two amino acids to get together is that you had to make a bend right there, right? And so the bends are going to force the protein to fold in a certain way. And so here's a small animation where the gold spheres are the hydrophobic amino acids. And if I hit play down here, notice all the hydrophobic ones are all going to try to clump together, and they're going to try to push the green ones out of the way as best as they can. We can make a bunch of different shapes and watch them as they kind of collapse on each other again. And this makes things like little loops, like this one up here has a loop and a loop and a loop, right? And that might be important for something that's happening in the shape of the molecule, right? So it's very, very complicated how the proteins fold. But when they do fold, they make a particular shape. The shape is then locked into place by the few that have sulfurs. If you get two sulfurs together, you make something called a disulfide bridges. And this is going to make this loop right here is now like locked in place, right? It was driven by the hydrophobic interactions, but it's held there by the disulfide bridges. The ionic bonds and the hydrogen bonds help as well to try to stabilize the shape. Finally, once you get the shape, sometimes multiple shapes, which we would call polypeptides, can interact together based on the hydrophobic interactions again, where some of the nonpolar amino acids didn't make their way into the center. They're stuck on the outside. But sometimes that's okay, because you want like say a section of nonpolar right on the edge here, so that will line up with a nonpolar section of one of the other polypeptides, and that will then make those two polypeptides connect and make a bigger superstructure, the quaternary structure, right? So here's a graphic that was from the first slideshow course that summarizes the whole thing. This is, if there's anything to remember, it's just these basic ideas. And that is the end. Let me know if you have any questions. Try out those quiz questions and ultimately the progress check.